So in this video, we're going to talk about vectors. So vector is a quantity that has both magnitude and direction. Okay, so both magnitude and direction. Now, typically, a vector is represented by using an arrow, kind of like this. So the length of the arrow tells us the magnitude. Okay, so the magnitude, and the arrowhead tells us the direction. Okay, so many quantities in physics can be represented by vectors. For example, the velocity of an aircraft can be represented by an arrow that points in the direction of the movement. So you got some airplane flying. Yeah, look how beautiful that airplane is, right? Okay. All right, so you can represent it by a vector just like that. Okay? So we introduce an arrow in the new direction. Based on this representation, it is not surprising that vectors and directed line segments are somehow related. So geometric vectors. So if P and Q are two distinct points in the xy plane, so we have some P and some Q, there is exactly one line containing both of those points. So I can draw one line that goes through both of them, and that's it. Only one line that does that, so maybe this is like line L. Okay? The points on the part of the line that join P and Q, including P and Q, are what's called a line segment. So this point from here to here, this is the line segment PQ. Okay? Ordering the points on so that they proceed from P to Q results in a directed line segment. Okay, so what does that look like? A directed line segment. So this is like from P to Q. So this would look like this here. So P and then Q. We have a little arrow directing it here. So this looks like PQ, just like that. Okay, kind of like what a ray looks like, okay? So the geometric vector is denoted here. This is the geometric vector, okay? In a directed line segment. So P is called the initial. This is the initial, so maybe I shouldn't do an arrow for that. We'll just draw a line down. So this is the initial point. And then this one here, this is the terminal, where it ends, point. Okay? So the magnitude of the directed line segment is the distance from the point P to the point Q. That's the magnitude. Okay? That is, it's the length of the line segment. The direction is from P to Q. If a vector V star has the same magnitude and the same direction as the directed line segment. Okay? So V, okay, you could call V equals PQ. Okay? The vector V, whose magnitude is 0, is called the zero vector. Okay? So the zero vector okay, this is V equal to 0. Okay? The magnitude is 0. All right, it's assigned no direction. Because it's not going anywhere. Okay, it's the 0 vector. So two vectors v and w are equal. So if two vectors are equal, then we say like v equals w. Okay? If they had the same magnitude and direction. Same magnitude, same direction, then they are equal vectors. Now, addition, so adding vectors. So vector addition is commutative. That is, what does that mean? V plus W equals W plus V. The order in which we add does not matter. So how do we add geometrically? Okay, so if we have some vector V that goes like this, and we have some vector W that goes like this, then to add V plus W together, what we do, so take, it's not copying, there we go. So to add them together, I take one, and I take the other, and I put them head to tail, tail to head, and the addition of those two gets me to this point right here, which is V plus W. Okay? Now, is it the same thing? Well, let's try W plus V. So I'm going to add W, and then I'm going to add V. And do I get the same thing? Well, if I put those together, clearly you can see that those get me the same thing. Okay? So that tells me that V plus W is W plus V here. Okay? So adding vectors, you start at the initial, you go to the terminal, and then you take that next initial and you put it right at the end of the terminal, head to tail, tail to head. Okay? Now, not only is it commutative, it's also associative. Okay, so it's associative. And what does that mean? That means that U plus V plus W is equal to U plus V and then plus W. Okay? So however we group them, whichever operations we do first, the order doesn't matter, it's associative. Still gonna get you there. Okay. The 0 vector maybe we call that 0. Okay. Has the property the vector plus the 0 vector equals the 0 vector plus the vector, which is still equal to just the vector. Okay? Now, if v is a vector, okay, then going in the complete opposite direction, this is negative v, same magnitude, okay? So v and negative v have the same magnitude, but the direction is opposite. Okay? The direction is opposite. So if that goes from like P to Q, okay, then this goes from Q to P. All right? Furthermore, if I take V and I add the negative vector of that, I should get the 0 vector. Okay? So if I'm going to do the difference, so the difference would be V minus W would be V plus the negative vector for W. Okay? So it's just going in the opposite direction. So if I have some V like this, and then I've got some W like this, now to do V plus W, well, what would that look like? That would look like this here, and I would get V plus W, okay? But say I did V minus W, that's V plus negative W, right? Well, what does negative W look like? Negative W looks like this. It's the opposite, right? Same magnitude, just the opposite direction. So how does that work? So V plus a negative W looks like that. So now this is V minus W here. Okay, very different. These two are not equal to each other. Okay, very different going on there. So multiplying vectors, all right, multiplying vectors by numbers geometrically. So when dealing with vectors, real numbers referred to as scalars, okay? Scalars. These are real numbers. Okay? They're quantities that have only magnitude, no direction. Okay, examples of scalars from physics are temperature, speed, time. Okay, so those are all examples. Okay, so now we define how to multiply a vector by a scalar. So definition, if alpha is a scalar and V is a vector, then the scalar multiple alpha V is defined as follows. Okay. If alpha is greater than 0, alpha V is the vector whose magnitude is alpha times the magnitude of V, and whose direction is the same as V. Okay? However, if alpha is less than 0, alpha V is the vector whose magnitude is absolute value of alpha times the magnitude of V, and whose direction, now remember the negative number takes my vector and turns it in the opposite direction, okay? Direction is opposite that of V, okay? So we have 1, 2, and 3. So 3 says if alpha equals 0, so if greater than 0, less than 0, and then alpha equal to 0, or V is equal to 0, then alpha V equals 0. Okay, so if we multiply by 0, a scalar by 0, multiply that by your vector, it's 0. If you take any number and multiply by a 0 vector, then it's also 0. So alpha V is equal to 0. Okay? So if you had some vector V here, and I multiplied that by a scalar 2V, now all of a sudden this vector is twice as long. Okay, it's still going in the same direction. Say instead, maybe I multiplied by negative 1/3. Well, instead of being 3 units long, maybe it's only 1 unit long, but it's in the opposite direction. Okay, so that's 1/3 V right there. Okay. So formulas here. 0 times V is equal to 0 vector. 1 times V is equal to V. Negative 1 times V equals negative V. If I have a scalar plus another scalar times a vector, then that's distributive, so alpha V plus beta V. If I have a scalar multiplied by 2 vectors summed together, I get alpha V plus alpha W. Okay, so it's distributed both ways. And then it's also associative. A alpha times beta V is equal to alpha beta times V. Okay? So graphing vectors can be entertaining. So let's graph some vectors. Okay? So say we have a vector V, okay, and we have a vector W, and we have a vector U, okay. All right, so say I want to do like I don't know, maybe I want to do V minus W. So v minus w. To do that, that's v plus a negative w. Okay, so I need to have a negative w, so I'm going to create a negative w. The only thing that's different here, instead of the magnitude is the same as the direction that swaps around. Okay, so let's do that. So a v, so I'm going to duplicate this. All right, and then plus a minus w. Let me put that back. All right, and so that gets me to right there. So this is right there. That is v minus w. Okay, so that's your answer right there. All right, let's try another one. Okay, let's do 2v plus 3w. 2v plus 3w. Okay, so v is right here. Now what v does is it goes over 3 up 2. Well, to do 2v, I go over 3 up 2 again. So really this is getting stretched out to right there. Okay? So let's do that. Let's add in another v to make it 2v. So v plus v, that's 2v, right? So that's 2v. Now 3w, let's duplicate this. So that's 1w, that's another w, and that's a third w. Okay. So 3w looks like this. 3w, add, right? Okay, so how's this gonna work? So this distance from here to here, that's 2v plus 3w right there. Okay. Now the last one that we're asked to do is 2v minus w plus u. So 2v, we already got 2v right there. So let's try 2v. Okay, so that looks like that. So that means go up to over 3, up to over 3. So that's right there is 2v, and then minus w. Minus w looks like this. We already got that. Okay. So from here to here, and then plus u. Add u to that. That gets me up to right there. Okay. So from here to here is my 2v minus w plus u. Okay. So we start at the tail and we finish at the head, and then we connect from tail to head until we get to our final destination. Okay? So and you just count your squares going from there. So that's how you graph vectors. So graphing vectors. Okay? Now, magnitude of vectors. All right, magnitude of vectors. So the symbol double bar V double bar represents magnitude of vector V. Okay? Since the magnitude of vector V equals the length of the directed line segment, it follows that the magnitude of vector V has the following properties. So this is the length of the line segment okay? So the length of the line segment has to be greater than or equal to 0. If the magnitude of the vector is equal to 0, this is true if and only if. If and only if means it works both ways. We have v equal to the 0 vector. That's the only way, okay? Another thing that's true, the absolute or the magnitude of the negative vector is equal to the magnitude of the positive vector. We know that to be true. Okay, if this is v, and then that means this is negative v, they both have the same length. Same length. Okay. And then the last case, the magnitude of alpha or of a, which is alpha v, is equal to the absolute value of alpha times the magnitude of v. Okay. Distance here is non-negative. Can't have a distance that's smaller than 0. Okay. One other one that's kind of useful is the unit vector. So a vector u for which the magnitude of u equals 1 is called the unit vector or a unit vector. So a unit vector has a magnitude of 1, right? That's 1 unit with a unit vector. All right. To find a position vector, to compute the magnitude and direction of a vector, an algebraic way of representing a vector is needed. All right, so an algebraic vector v is represented by v equals a comma b, these little brackets, all right, where a and b are real numbers okay, so they're real numbers, scalars, called components of the vector v. Okay? So if you had go out a here and up b here to get to that point there, this is v, which is equal to a comma b. That's that vector right there. So a rectangular coordinate system is used to represent algebraic vectors in the plane. So if your initial point is the origin, then this point right here, the ending terminal point, is going to be your A comma B. Okay, so that's starting. You don't have to start at the origin, but that's where we start with this picture here. Okay, so something to keep in mind there. Now, there's a theorem. Suppose that V is a vector with initial point P1 equals x1 minus y1, and it's not necessarily the origin, because we don't have to start at the origin. It makes it nice if we do origin 0, 0. And our terminal point P2 is equal to x2. Sorry, this should not say minus in between. It should be a comma. x2 comma y2, just like that one. Okay? So we just have some initial point x1 comma y1 for the starting P1, and some ending point P2, which is like x2 comma y2. Okay? So if V is equal to P1, P2 vector, then V is equal to the position vector. Now, the position vector is whenever we are initial point at the origin. Well, how do I make the position vector get shifted to the origin? Okay, well, that would mean that I would need to move this over here, and I'd need to move that down here. So to do that, I would have to subtract x1 from the x component and y1 from the y component. So then what would that become? The new point, the new piece, would become 0, 0, and this would be x2 minus x1, and then y2 minus y1 for that new v. Okay, we'll call it v prime. That's the position vector. So this would be v equals x2 minus x1 and y2 minus y1. Okay? So you can literally, the only thing that matters with a vector is the length, the magnitude, and the direction. Once I have that, I can move that vector anywhere I want in my space, and it's still the same vector. The only difference is this vector is a position vector, okay, because it starts at the origin. All right, so it's the same, so it's same vectors. Okay, so that's the same as that vector right there. Okay? Now, finding a position vector, how, kind of showed you a little bit arbitrarily, but I want to show you, what you can do. So finding a position vector. All right, so say you've got V equal P1, P2, where P1 is equal to negative 1, 2, and the second point, P2, is 4, 6. Okay? So negative 1 and then up 2. And then 4. So 1, 2, 3, 4. And up 6. 1, 2, 3, 4, 5, 6. All right. So that's P1 and that's P2. So what we really want to do here is I want to know what is this vector here. Okay, what is that vector there? Well, how do I get down here? Well, I know that that's 0, 0, right? Okay, so really all I need to figure out is what this piece is. Well, how do I do that? How do I get from there to there? Well, to find this, it's x1 minus x2, comma, y1 minus y2. That's it. So that's my x1, that's my y1, that's my x2, that's my y2. So I'm subtracting things with the same color highlighter. Okay, so this this point right here, this 4, 6, okay, I need it to go over. So 4. I've written this backwards. All right, so I want this to be x2 minus x1, y2 minus y1. Sorry, guys. Okay, so that's 4 minus a minus 1. And then this second piece here is 6 minus 2. And so what is that equal to? That's 5, 4. This point here is 5, 4. All right, so the position vector is V equals 5, 4. Okay? Equality of vectors. So we have a theorem here. Theorem is called the equality of vectors. All right, equality of vectors. So two vectors, V and W, are equal if and only if their corresponding components are equal. Okay, what does that mean? If V equals A1, B1 and W equals A2, B2, then V equals W if and only if, that's what this double arrow means, the first component equals the first component here, so A1 equals A2, and then the second component, B1, is equal to this second component here, the second one, B2. Okay? So if that's true and this is true, then V is equal to W. Okay, so each component has to be the same. Now, there are letters that represent certain things. So in physics, it's typical to let I denote the unit vector whose direction is along the positive x-axis, okay? And J denotes the unit vector whose direction is along the positive y-axis, okay? So this point 0, 1 would be the j vector, and this point 1, 0 would be the I vector. All right, that's typical in physics. So if you had a V equals AB scenario going on, this would be A and then 1 comma 0 plus B 0 comma 1, which is the same as A, and then this is a unit vector. So this right here is a unit vector in the positive x direction, so that's AI plus the B, the scalar here, times the unit vector in the y direction, that's BJ, okay? So the quantities A and B are the horizontal and vertical components. So horizontal, vertical components of V. All right. So how would I represent, say I had some 5 comma 4, this would be represented as 5I plus 4J, meaning I go 5 units in the positive x direction and 4 units in the positive y direction. Okay, so that's that vector V right there. The difference, this is a point, this is a vector. Okay, so be careful, those two things mean, those are different. Different. All right? So adding and subtracting vectors algebraically. The sum, difference, scalar, multiple, and magnitude of algebraic vectors are defined in terms of their components. So I'm going to let V equals A1I plus B1J, which is equal to A1 comma B1. I'm going to let W equal A2I plus B2J, which is A2, B2. I'm going to let those be two vectors and alpha be a scalar. Then V plus W is equal to A1 plus A2I plus B1 plus B2J, which equals A1 plus A2 comma B1 plus B2. Close it up. V minus W is A1 minus A2I plus B1 minus B2J, which equals A1 minus A2, comma, B1 minus B2. And then alpha V equals alpha A1I plus alpha B1J, which equals alpha A1, comma, alpha B1, close it up. The magnitude of V is equal to, well, we use the Pythagorean theorem here. If V goes A1 in one direction in the positive axis this way, and then B1 in the y direction, then this distance here, Pythagorean theorem says A1 squared plus B1 squared, and then I take the square root there in order to get my magnitude. It's an application of Pythagorean theorem. Okay, so these are a summary of techniques. All right, so we're going to apply these techniques to a few problems now. So geometrically, let me throw in all right, so let's do this can be W, and then this can be V. Okay, so if I'm going to add together W plus V, that gets me from here to here. So this little piece right here could be A2, and then that means this little piece right here would be A1. So A1 and A2 added together, same thing. This could be B1, and then this piece here, that's B2. And if I add those together, I get from there to there. Okay, so that's W plus V. If I took V and I multiplied it, so maybe I doubled it, then this is the scenario. That's 2 times V. Okay, that's double the length. All right, so if this was A1, then A1 plus A1 is equal to 2A1. And if this was the height, that's B1, and then another B1, that gets me 2B1. So this becomes 2A1, comma, 2B1, which shows me my alpha V equals my alpha A1, comma, alpha B1. Okay. Let's do adding and subtracting. So add, subtract. So V equals 2I plus 3J. this is 2 comma 3, and w equals 3I minus 4j. That's 3 comma negative 4. I want to find v plus w, and I want to find v minus w. So to find v plus w, I'm going to add the I components. So this is equal to 2 plus 3I, and then plus 3 minus 4j. Okay, and what is that equal to? That's 5I, and then plus a negative 1j. So that gives me 5I minus j. All right? If you want, you can convert this to 5 comma negative 1, just like that. Now if I'm going to do v minus w, this is 2 minus 3I plus 3 minus a minus 4j. And so this gets me negative 1I plus, and then minus a minus makes a plus 4, and so that's 7j. So that's negative 1 comma 7j right there. Okay? So exactly how you would think to add and subtract. Now, finding scalar multiples and magnitude of vectors if v equals 2I plus 3j, that means that it's 2 comma 3, and w equals 3I minus 4j, that means 3 comma negative 4. Then I want to do 3v. Now 3v would be 3 times 2I plus 3j, which equals 6I plus 9j when I distribute the 3, which is equal to 6 comma 9. Okay. The next one I want to do is 2v minus 3w. Now this would be 2 times 2I plus 3j minus 3 times 3I minus 4j. Simplify here, that's 4I plus 6j minus, and then 9I, and minus a minus makes a plus, 12j. Okay, 4I minus 5I, 9I makes negative 5I, and then 6 and 12 make 18j, which is equal to negative 5 comma 18. Okay. Now, if you were asked to find the magnitude of v, v has horizontal component 2, vertical component 3. So to do this, I get the magnitude of 2I plus 3j, which is equal to the square root of the component squared summed. Okay. Which is equal to, well, that's 4 and that's 9. That makes square root of 13. All right, and you don't have to simplify there unless you just want to throw it in the calculator. It doesn't simplify. All right, so one thing we talked about the unit vector, but now we're going to talk about how to find the unit vector. So the unit vector in the direction of v, okay, for any non-zero, so this doesn't work with the zero vector, it's not, zero vector can't be a unit vector, okay, unit vector u is equal to v divided by the magnitude of v, okay, this is a unit vector that has the same direction as the original vector v, okay? So it has the same direction as the original vector v. Now if I multiply both sides by the magnitude, I end up with the equation v, the original vector, equals the magnitude of v times the unit vector, which if you multiply by 1, you don't change anything, right? So this is the unit vector. Now, this says if u is a unit vector in the same direction as the vector v, okay? Unit vector in the same direction as v, okay? So how do we find a unit vector? Well, let's work through an example. Find a unit vector in the same direction as v equals 4i minus 3j. Okay. Well, first, I need to find the magnitude of v, because u equals v divided by the magnitude of v. Well, I've got v, right? So I got the numerator. I just need to find the magnitude of v. The magnitude of v is the square root of 4 squared plus 3 squared. Okay, I just square that distance, right? Get my triangle, Pythagorean theorem. 16 and 9 makes 25. Square root of 25 is 5. So that makes that pretty easy. Okay, so now I multiply, right? This is equal to 4i minus 3j divided by 5. So what does this equal? It's 4 divided by 5i minus 3 divided by 5j. Okay? This right here is my unit vector. That is the u. Okay? Now if you wanted to check, you could. The magnitude of u equals the magnitude of v over the magnitude of v, which is equal to the square root of 4 over 5 squared plus 3 over 5 squared. Now, if I do that math, that gets me 16 over 25 plus 9 over 25, which is equal to 25 over 25, which is equal to square root of 1, which is equal to 1. And therefore, it is the unit vector. That magnitude does equal 1. That's a unit vector. So this is to check. Okay? All right, so find a vector from its direction and magnitude. Okay, so how to find a vector from its direction and magnitude. So if a vector represents the speed and the direction of an object, it is called the velocity vector. Okay? Represents speed and direction of an object. Okay? So if a vector represents direction and amount of force acting on it, it's called the force vector. So the force vector represents the direction and amount of a force acting on an object. In many applications, a vector is described in terms of its magnitude and direction rather than in terms of the components. So for example, a ball thrown with an initial speed of 25 miles per hour at an angle 30 degrees to the horizontal is a vertical or a velocity vector. Okay? So suppose that we are given a magnitude equal to v naught of a non-zero vector v and the direction angle alpha. So alpha is going to be something between 0 and 360. Okay? Between V and I. All right, to express V in terms of the magnitude of V and alpha, first find the unit vector having the same direction. Okay, so say we've got, some unit circle. Okay, so we know what a unit circle looks like. So I go out some I in this direction and up some j in that direction. So the unit vector, okay, to get this u here with an angle of alpha, how do we get this point? Well, that's the cosine of alpha comma sine of alpha. Okay? So you knew somewhere that trig was going to be coming back into this, right? So in reality, this v vector is probably somewhere out here, right? So we need to get this back. We need to get this down to the unit vector. So that's v over the magnitude of v. Okay. So to get this u vector here, u is equal to cosine alpha sine alpha. Okay, so what does that tell me? Well, that tells me v equals the magnitude of v times the cosine alpha of I plus the sine alpha of j. Okay? So all we did there was we solved this equation for v. We multiplied by the magnitude of v on both sides. All right, so let's work through a problem. So finding a vector when its magnitude and direction are given. Okay? So a ball is thrown with initial speed 25 miles per hour in a direction that makes an angle of 30 degrees with the positive x-axis. Express the velocity vector v in terms of I and j. What is the initial speed of the horizontal direction? And then what is the initial speed in vertical direction? Okay. So, what's important here? Well, the speed is 25 miles per hour. Okay? So the magnitude of v, is equal to 25 miles per hour. And the angle is 30 degrees. So the angle between v and the horizontal I, okay, the positive x-axis, is alpha equal to 30 degrees. So what does that tell me? That tells me by my equation, v equals magnitude of v times the cosine alpha I plus the sine alpha j. This is equal to 25 multiplied by the cosine of 30 degrees I plus the sine of 30 degrees j, which is equal to 25 times square root 3 over 2 I plus 1/2 j. Okay? And so this gets me 25 square root 3 over 2 I plus 25 over 2 j. So that's the first part. We just answered the first part. V in terms of I and j. Got that. Okay, so we got that going on right there. Now the second part, what is the initial speed of the in the horizontal direction? So what's the initial speed in the horizontal direction? Okay, this component is the first component, the 25 square root 3 over 2. So that's 25 square root 3 over 2 is roughly, if I type in my calculator, 21.65 miles per hour. Okay, what is the initial speed in the vertical? That's 25 over 2, which is 12.5 miles per hour in the vertical. Okay, so those components, those are the initial speeds. All right. Now, say we have, we want to find the direction angle alpha. Okay, so finding the direction angle of a vector. Okay, so find the direction angle of a vector. So say we have v equals 4i minus 4j. So what does this look like? Well, 4, so 1, 2, 3, 4, and then j down 1, 2, 3, 4. So my vector goes like this. That's my vector v. Okay, to the point 4 comma negative 4. So that's component 4 comma negative 4, close it. That's that point P. Okay, now alpha is this angle going through here. So how do I find alpha here? Okay, because remember alpha is stuck between 0 and 360 degrees. Okay, well how do I do that? Well, I can actually use trigonometry here. Okay, if I draw a right triangle, okay, and I take some angle theta in here, okay, so I go over positive 4 and down negative 4. And so what's that going to do for me? Well, I can use the trig function tangent theta. Is how does tangent relate? It's opposite over adjacent. So negative 4 over 4. So that's negative 1. So if I do theta is the tan inverse of negative 1. Okay. That's going to get me, well, type it in my calculator. Tangent inverse negative 1. Okay, I think that's pi over 4. Yeah, so negative pi over 4. So this gets me negative pi over 4. Okay, now negative pi over 4 is not between 0 and 2 pi. So pi over 4 is 45 degrees. So instead of doing negative 45 degrees, I need to subtract that from 360, full circle. So 360 minus 45 degrees gets me 315 degrees. So this angle alpha is 315. Okay, so alpha here is 315 degrees. Okay, so that's finding the angle. That's how you find the angle right there. All right, so these next examples, they are applications.